because there was some email about pastries on the 8th floor meeting. But
Did you go over there?
no, that's what I'm saying. I'm here.
Oh,
Sacrificing free pastries.
well, you could have gotten some for all of us.
True.
You are screen sharing. Present to everyone.
We could wait for you. You could wait for me.
Hi. All right. Well, this is like a crazy.
I think so.
Let's also screen share with these people.
Alice is generous, but I don't know if she's that generous.
Well, you guys missed it. There was no network connectivity in 35 Neelan for like 15 to 20 minutes, which means that you can't do anything. No email, no server, no internet.
So it was just solitaire.
Well, they don't put those on the computer anymore.
Oh.
So no solitaire
Maybe
either.
not on your computer.
Exit full screen. I want to share. Where are you? Share screen. Share screen. Share my entire screen. Google Hangouts is sharing your screen. Perfect. Hide. I think that I'm broadcasting to YouTube. This amazing infinite thing. Who else do I feel like that? And then is that it? I guess we can wait for that.
Yeah, we had a pretty sparse class, in-person class.
Right. Yeah, because Alex is remote. Alex, are you here?
He was remote before.
I've
Tamar
invited
wasn't with
him.
us.
Tamer, I know, is
It
not.
looks like he's here. I see him.
Yeah, I see.
Oh, okay. Wait, you see him?
Well, there's a picture down below.
Yeah. Down, you can see him.
Oh, Alex. I see Alex. Hi, Alex. Teresa. Lauren?
Yes.
Oh, hi, Lauren. I just don't see your picture, so it's so exciting to hear your voice.
It's because there are so many of us that it only shows a couple of them now.
Oh, okay. Okay. So now I think that we're all here. So today we're going to talk about how to actually create a propensity score. And we have the data set that goes along with that article that you guys read, the right heart catheterization one. So we'll play a little bit with how to not exactly recreate what they did, but at least using some of the similar variables and the exposure and all that stuff. And then we'll learn how to apply the propensity score as well. Is anybody doing a propensity score for their project? For their thesis?
Later on with the idea, but it's too complicated.
I'm not doing one for my thesis, but I'm doing one for something else.
Right, true. Okay, well, who knows? Maybe you suddenly will incorporate it when everybody's like, there's too much confounding in your study by indication, and you should do a confounding score, or propensity, score. I like confounding score too, though. Maybe I can come up with that. So I'll kind of skip over. We obviously know when we're supposed to use a propensity score, and the disclaimer, of course, being that it is not a cure-all for confounding, and that confounding can still remain after the propensity score. So here's some things to consider kind of when you're thinking about how to build the score. So you want to include, obviously, confounders of the exposure outcome relationship. And you want to include covariates that are associated with the outcome and the treatment allocation. And it's you can include interactions as well as nonlinear associations. And of course, the biggest thing is that you don't include things. Well, this isn't the biggest thing, but an important thing is you don't include anything in your propensity score that occurs after the exposure. So that is only include things that occur before the exposure. And I just gave you that example on Monday, right, with somebody doing like a propensity score for gender or something like that. Wasn't that? Does that sound like it was familiar or no? No? Propensity score for like a bad example of a propensity score? No? Okay. Never mind. And then you don't usually include variables related to the exposure, but not independently related with the outcome. So this would be like you don't include something that would be an instrumental variable. And you also don't need to worry about including too many variables unless that creates no overlap. So if you specify so well who's in each of the exposure groups, then there won't be overlap. And then the way that we actually are going to build it is we fit the model to predict the exposure of interest, and then we're going to use that propensity score then in some way in the model that is looking at our outcome. And then the way that we check our propensity score is to see whether there's sufficient overlap between each of the groups, and then also look at the C statistic. And you don't want the C statistic to be perfect because that would mean no overlap. And you also don't want it to be terrible either. So again, we're going to use that right heart catheterization data set where it was looking at the association between right heart cath on the first day of hospitalization and then whether or not they died by 180 days. So we know that there could be confounding by indication for the right heart cath. So we want to be able to create a propensity score to hope to control for some of that confounding. So let's read in this data set. Hopefully this is. Oh, I really thought I had gotten the right working directory finally, but I didn't. Pub. No, I'm just guessing. Oh, what is it? Whew. So if you're on one of these computers, it's actually hhsl-pub is the working directory. And then here's our right heart cath data set. And so we see that there are like 5,700 observations for that. And let's look at a summary just to get an idea of what we have for missing data. So there's like, what do we say, like 60 different variables. So there's a variety of, let's see, so the NAs. So what are some of the variables that have a bunch of missing data? Oh, it looks like this cat2 does. The other thing is, I guess unless you printed this, you won't know this, but at the back of the lab document, there's kind of like a data dictionary that includes all the variable names as well. So this, for example, this cat2 variable is the secondary disease category. So because it's a secondary disease category, it's going to be missing for people that don't have that secondary disease. So we were missing like 4,500. So that's going to be a lot of missing data, obviously, given our data set only has 5,700. What other things do we have? Yeah, I think there's some other like measures. Yeah, some of these ones that are measures. What is this one? Oh, this is a daily living thing. So anyways, there's some missing data that we need to kind of, we don't want to consider those variables in our propensity score. Let's see. So what I'm going to do actually is I'm going to remove the variables from our data set that have a lot of missing data. And then what I'm going to do is restrict the data set to a data set that has no missing variables in it, so that, or no missing data in it. So it'll be easier for us to work with the data set. Again, always be mindful if you're just throwing away your data. Don't just do that. If this was your real project, you might consider doing multiple imputation or something like that to get values for everybody. Or you could do like a complete case analysis and then a sensitivity analysis with imputation or something like that. So this is, I'm not sure if I've showed you how to do this before. Maybe I have. But there's a way to get rid of just a few variables using, we can do this subset command. Then I say what the original data set was, and then select. And this is a way to, if you put the minus sign in front of it, it's a way to get rid of those variables. If there were no minus sign here, it would just keep those variables. But since there's like 60 something variables in here, I don't want to have to write the names of like 59 of them or whatever. So the opposite is we can just delete them or get rid of them this way. So I'm just going to overwrite the original data set. So these were 3 that I determined had a lot of missing data. So just remember that see that there's 63 variables right here. Then if I were to run this line, now there's just 59. So I've gotten rid of those 4 that had a lot of missing data. Then what I'm going to do is use this NA-omit, which gets rid of any of the observations, any of the lines of our data that have any missing data in it. Again, this is just so that our data set's easier to work with when creating the propensity score and stuff. So I'm going to do that. Notice again, I'm overwriting the original one. We originally had 5737. Oh, we only ended up getting rid of one person. So most of the missing data, again, was in these 3 variables. The other thing I'm going to do is, so the 2 outcomes or the 2 variables for the exposure and the outcome are currently like, they're binary variables. They have 2 levels, but they're defined by like words as opposed to zeros and ones. So I don't really like words. I just want it to be 0 and 1. So I'm going to create those 2 new variables. So this is the one for right heart cath. So I'm going to, again, do the as numeric thing, turn anywhere where it has this, what do they call it? They call it swan, right?
Swan guns.
Yeah. So that's the name of the variable actually for the treatment, for the exposure. But I'm going to make it wherever it's equal to right heart cath. I'm going to turn it into a 1 for this new RHC variable. Same thing for death. It originally was this variable called death with yes and no. So again, I want to just make that defined as binary variables. So we can look at a table just to get an idea of how many people are in each group and what proportion are dying in each of the exposure groups after or before any adjustment. So as an example, let's see, did I do row or column percentages here? Row. Does that make sense for how we would interpret this, or how would we interpret these?
Yeah, that makes sense. So the proportion dying per exposure.
Yeah, so that, I think it makes sense. So among the right heart cath group, 68% are dying. And then among the non-right heart cath group, 63% are dying. So it looks like, you know, getting the right heart cath is bad based on this. I mean, no statistical test going on or anything like that, but just looking at the raw numbers. So before.
Is that the other way around? I just want to make sure, because I think they're the people that survive.
Oh.
It depends on when you're looking at it, because if you're looking at 30-day, I just want to make sure on the.
This should be right, because there's a variable called, this is a variable called death.
That's right, because RHC is bad.
No, I know that it's just the numbers, because
Oh.
when we
Gotcha.
yeah, because on table 2.
From the paper. This is also 180 day, if that makes it any.
Oh, it's 180. Okay, my bad.
Yeah. That's okay though. Good to question things. So yes, we have more people dying in the right heart cath group as of now. So let's begin by fitting just like an unadjusted logistic regression model and get what the odds ratio is, so that we can then compare that to what we get when we start doing our propensity score. So just using our GLM that we've previously used with the binomial and the logit link. Let's run that. Let's get the odds ratio. So what's the odds ratio then for right heart cath?
1.25.
Right, and it's obviously showing that right heart cath is associated with increased odds of death. And then our p-value is quite small, so obviously this is a significant finding. All right, so now let's build our propensity score. So I've got this little table going, and I'll gradually add more odds ratios onto it once we fit different types of models with a propensity score, so that we can see how the results change. All right, so what variables did they use in the Connors paper? That was the one you guys looked.
Tons.
Yeah, okay. That's a good answer. So yes, they use a ton of variables. At first I was like writing them down, and then it was like a really long paragraph. So I didn't write them all down, but they use a ton of different variables. So we're not going to do all of the variables that they did. We'll just I kind of picked a random subset of them just for practicality purposes. So the first step of our propensity score is to do the logistic regression model with the outcome being the exposure. So I've decided to include in our propensity score, we're going to include age, sex, insurance, primary disease category, history of cardiovascular disease, Apache score, creatinine, and blood pressure. You may have selected other ones to include, but these were the ones that I chose. So all we need to do is fit, I've actually named this one, the name of the object PSM for propensity score model, although just so that I would remember that's what it was. So here's all of our variables in it. I did do a summary of the model, though it really doesn't necessarily matter because you're not really interested in like interpreting or doing any sort of inference on this. You're just interested in controlling for or building the propensity score with things that we think are associated with the exposure and the outcome that might be confounders. You can sometimes I know that in the paper, I think they looked at like interactions and all that stuff, which you can also put into your propensity score model, though again, I kind of did a more simplified version. All right, so then remember the propensity score or the predicted values of a logistic regression model, those are going to be the probabilities. So the fitted values that we get out of that are the probabilities, which is literally what the propensity score means, which is the probability that they have the exposure. So we can save that. So we fit the model right here. And then we can save the fitted values from this model as a new variable and just add it onto our original data set. So that's what this step does right here. And I'm calling it PS for propensity score.
So the dollar fitted values, that's like a thing of all GLMs.
Yes.
So.
Yes. And most models produce that as well. We did that in linear regression. We could get everybody's fitted value for the outcome doing this. So yeah, this is, and in fact, if I look at
the fitted value, the log, who's already done all that for you.
Yes.
All that stuff.
Yeah.
Okay, so because this is the log odds. I would have thought that would be the log odds of the.
So it actually gives you out the probabilities.
Nice.
So yes, it's very nice of it for us. And yes, as you mentioned, so if I were to take the names of this PSM, which is the model object that I just created, you'll see that somewhere it should say, the fitted values. These are actually the fitted values related to it. These are things that are with, just like a data frame or data set has different kind of pieces to it, so does the model object. So these are all different parts of this model object that we could do a $sign and then any of these and get this stuff out.
So just so the PSM basically, when you do fitted values, that is exponentiate your thing.
Yeah.
And then 1 minus all that. So that
it's already done all of that. It's 1 plus the exponentiation, but yes, that same idea. It's already done all of that for us. And in fact, that's why I think it was last week when we were doing some of the diagnostic for logistic regression, when we wanted to look at something, it was like we plotted the log odds or something like that. And we had to undo all of this with the fitted values to get back to the log odds because it was in the probability world. So we can do a summary of the propensity score just to get an idea of like what values it's taking on. Oh, I should ask you ahead of time, what values would we expect, or what are the range of possible values for the propensity score? 0 to 1, exactly, it's a probability. So for the distribution that we have for the propensity score values go from the minimum is just under 4%, and the maximum is almost 90%. That's actually a pretty wide range. I think it's because there's a fair amount of variables that we've included, so there's a lot of that range that it can get. But you see the median and the mean are both around like 37, 38. All right, so then what else did I do? Oh, and we can also look at we can separate out the propensity score by each of the treatment groups. So we can look at what the mean propensity score is in those that did get right heart cath and those who did not. And remember, we did this, we could use the t-apply function. Remember that? We can do whatever the continuous variable is, then the group variable, and then we want to take a summary of it. So that will give us this. So you can see, as we would expect, the propensity score is higher within those that are actually getting treatment, which is, of course, what we would want to find. All right, so the other things that we want to do to kind of check the propensity score. Actually, how did the Connors paper check the propensity score?
What do you mean by check?
So to see,
Area under the curve.
so the C statistic is a way to check it. Did they report on their C statistic?
Yes.
Did
What was theirs?
like 0.83 or something?
Okay, yep. So that's a good C statistic. And then you can also look at when you divide it into like the quintiles, and you can compare. So you divide it into quintiles by the propensity score. And then within each of those quintiles, you can compare the treated and the non-treated as well to see whether, so they should be similar. You're expecting them to be similar within the quintiles. So that's another way that you can look at, kind of check it that way. And you're kind of looking for balance in between, you know, after you've created the purpose of the propensity score is to be able to create balance in those quintiles.
What's up? Yeah, we hear that if it's 0.5, like we got that, that's wrong. If it's close to 1, how close to 1? How much overlap or?
Yeah, so that's a good question because it's one of those things that's like, oh, you don't want it too close, like it's very vague as you're picking up on. So I mean, I wouldn't want to say a single number. There's not a single number that you can like be like, that's too good, that's not good. But when we start, I think a better way is actually to also look at the histograms of each of them and actually see if there's overlap that way as well. Is another way to kind of visualize that one. As
how much overlap?
So
mentally, I'm like, if you could distinguish, even if it's 20 or 30 in a completely biased like prediction model, so it only works for this data set, is that I'm struggling with like where it's bad, or at what point is it bad? If 0.85 is good,
right.
0.9 good, 0.95.
Yeah, I mean, I would think that once it gets into the 0.9s, it's starting to get not as good, with it being so good that it's too good.
Okay.
That's kind of just my own impression, though. I don't like quote that into your like thesis or something like that. Personal communication with Angie.
And it would be wrong to be like, oh, we're at 0.9, we'll just take out a variable. Or
I mean that would create less overlap, or that would create more overlap.
yeah.
So, I mean, I don't know. Yeah, I mean, I think that has to do with, yeah, you don't want your model to be too good. You don't want to perfectly fit it, which is why, I mean, you don't want to include like an instrumental variable in it or something that would perfectly differentiate between those groups.
Okay.
Because the idea is that you find the people that have, you know, similar propensities to be getting the treatment, and so that you can compare those ones to each other. Okay, so, we can look at our C statistic. Remember, we have to install this other package to be able to do that. It's this RMS package. And then you can do the LRM function that's part of that. And where is that? So I have to install the package. Or maybe it's already here. Nope. Wishful thinking.
You must, I mean, because we only really know what packages you tell us. Because
You know, so brand surfing?
Yeah.
There's so much stuff. Do you have like I'm sure you do this, like, do you have like a package glossary? Like, you know what you did for us for the start of the year, at the start of the year? I'm not saying if you don't, obviously, that's also great. It's scattered.
Yeah, no, I don't have one single package library, although, I mean, maybe I could have a package library.
No. That's definitely not what I like, because clearly a billion lines of code per class is enough work.
Right. Well, I think that the thing is that you just want to know when you use a specific package, because you don't need to install every single package, you know, all at once. And sometimes, annoyingly, there's similar functions in different packages. And if you like install one and you think you're doing the other, like you can get errors, and it's a weird like thing like that because it's open source. So people are just like adding stuff, and there's no oversight to see whether it conflicts with other things that are out there, other functions and things like that. But, you know, if you're like doing a logistic, you know, you're doing a propensity score, you probably need to go back to this lab anyways, and this is where you'll find the package that you need. I mean, I have a little bit my own personal, like I know some of the common packages I use, but, and like once you, the thing that's annoying / not annoying / annoying is that when you're, every time you reinstall R, you update your version, it like wipes out your package library or whatever. So anything that you've downloaded. So I keep a little bit of a list so that each time I update my R, I can just automatically install the packages that I use a lot.
Oh, nice.
But, and then only load it into the library or whatever when you need it. Okay, so RMS, I installed that. Click on this so I can get my LRM function. This is that, okay.
Now, is this LRM just specifically because we're trying to create a C, or we're trying to calculate the C statistic? Because otherwise, LRM versus GLM, I mean, it's doing the
Yes.
same thing, isn't it?
Yes.
Okay.
Yes, for some reason, the GLM doesn't easily give us a C statistic.
I asked why LRM now as opposed to GLM, because they're both logistic regression. So it's just asking whether or not the LRM was just specifically because we are trying to get a C statistic.
Yes. So this is like a quick way to do it. Although this LRM doesn't create as many of the like nice things that the GLM does. I almost don't, it's like harder to get out the residuals, I think, and like fitted values and all that stuff. So typically we use the GLM. This one, remember, also gives us that model likelihood ratio test, just comparing the fit of the overall model, which was one of our model diagnostic things that we talked about in the past. So what do you think about our C statistic?
Bang on.
Hmm?
It's close to that.
Yeah, mediocre,
Yeah.
which is just what you're looking for.
That's pretty mediocre.
Oh, so then we can look at, we had talked about the overlap in the two groups. So we're going to plot the histogram of separately by whether somebody's in the right heart, the cath group or the not cath group. So one way to do this is we're going to do a histogram. So I'm going to do a histogram and subset it. I'm going to do it of the PS variable, and then I'm going to subset it to people that are in the treatment group. And then I'll do a second version where I subset it to people not in the treatment group. And I'm stacking, I'm going to do that par thing where I tell it how many like panels of graphs that I want. And this will create 2 rows of graphs and 1 column. So it'll stack them right on top of each other. So it'll be easy to compare. The other thing I've done is I've made sure that the axes are the same, because R just automatically creates the axes based on where the data are. So this 0 to 1 will ensure that they both have that, they both are on the same axis. And for some reason it doesn't like this. Oh, well, if I move it out, it should work maybe. Why doesn't it like the figure margins? So other people having these issues?
Nope.
Ah, there we go. Just needed to make the plot area big enough. So here we're looking at overlap. So Henry, what do you think about the overlap?
Bang on.
Hmm?
Great overlap.
Great overlap. Great enthusiasm. Yeah, so I mean, there's decent overlap here. It's not like there's some area where there's a ton of scores and no scores in the other area or something like that. So yeah, it looks to be pretty much wherever there's somebody in the top group, there's somebody in the bottom group. Maybe, yeah, even out to the extremes of it as well. You do see, obviously, that there's, you know, more people with the lower scores within the no right heart cath group, but that would be, you know, expected. Okay, so then what can we do? Oh, you could also, so that plot that I just did, that was on the propensity score scale. We could also make it more normal by going to the log odds scale if we wanted. So we just undo the probability basically by going back and forth between the log odds and the probabilities using the equations that were in the very first logistic regression lab. So we can go to the logit or the log odds of the propensity score by taking the log of the propensity score over 1 minus the log of the propensity score. Again, this is just kind of a given equation. So that will add on to our data set. And then we could also have done the plots with this logit PS for the on the log odds scale. So these ones look a little bit more normal. But again, we're still looking for overlap here. And I'm on the same scale. Okay. All right, so next, let us, here's the log odds. Let's actually divide it into the different quintiles. So those are the 5 different groups. So we're gonna divide them into 5 groups based on the propensity score. And we're gonna, to do that, we're not gonna pay attention to which exposure group they're in. We're just gonna, take a continuum of the propensity scores and find 4 different cutoffs that will put it into 5 groups. So within R, there's this function called quantile. And this will give you the different quantiles of the data. And so here's the function quantile. We tell it the function or the variable that we want it to divide into quantiles. And then we tell it which quantiles we want. So because we're doing quintiles, those are, each one is 20%. So that's what I've done right here to get each of the cutoffs. So I need a cutoff at 0.2, 0.4, 0.6, and 0.8. And I'm also going to store it into this thing called quint for quintiles so that I can refer back to this object. So I'll do this all at once and then we can look to see what it has. So run that. That's now appeared somewhere over here in my value or my, objects over here. If I were to print out this thing that says quint, oh no, then you freeze R. All right, then you open another version of R.
Do the quintiles, presumably there'll be unequal sizes, the quintile sizes.
What do you mean by unequal?
Well, I mean, they'll be equal in the sense of, from the number of participants in
Yes.
each quintile. Could you set the quintile instead of by the probability, have the probability set by 1,000 patients, you know what I mean? So then you have 5 equally sized.
So we're going to get 5 equal. There's going to be even number of people in them.
Oh, yeah.
Yeah, that's what quintiles means, that you divide the data into 5 evenly sized groups. Similar to like the percentile thing when you have the median or the 25th percentile. So it's the same number of people in each group, but the cutoff is not going to be like even.
Yeah.
The propensity score
So
cutoff.
Quint creates 5 equal sized groups.
Yes.
So it's not cutting off at
At a
a
probability.
propensity score of 0.2.
Yes, that's the yeah, so it's a little bit confusing because the propensity score is a probability, but this is also using the probability.
But that means that it doesn't handle, so like with Sprint, we had a problem where it doesn't handle ties very well. So you could have people of the same propensity score and be in 2 adjacent quintiles.
Yes, and I will make a comment on that, is that once you have a lot of variables, especially continuous variables in your propensity score model, the likelihood of having ties here is low because you can get, decimals out, there's a lot of options for where people will be. All right, so let me try this again. Oh, well, this isn't super. What have I done? all right, so I feel like I didn't do all my steps or something. Do this, do my propensity score, added my propensity score.
Works okay on here.
Hmm?
It works perfectly. Like,
Okay. Quintiles, let's try this. Okay, so maybe now I'm good. Okay, so now it's giving us the propensity score cutoff for each of these, to define each of these quintiles. So for the 20th percent, it's around like 21%. For the 45th, or 40th, it's around 33, 42%, and then 54. So clearly these aren't evenly spaced.
So that's awesome. So this is ranked your 5,734 patients by their probability,
Mm-hmm.
and then cut them into 5,
Mm-hmm.
and then gave you the average probability of each.
The cutoff probability.
Cutoff probability, okay.
Yes.
From 0 to 0.21, 0.21,
And then
0.32.
Yes.
And then you can just subset. You can subset like quintile 1, and then
So I'm going to, rather than subset, I'm going to create a variable to define which quintile they're in, which is the next step. Great lead in. All right. So what I'm going to do is I am going to define this new variable that I'm going to attach onto my original data set, and I'm going to call it ps_quint for quintile. And then what I'm going to do is I'm going to use the square brackets, which is kind of like I'm subsetting it in a way, but I'm not like creating a new data set to that. So I am going to say wherever somebody has a propensity score that is less than the first object in my quintile object, then I want to store in a 1. So the reason, so I could have just, bless you, copied this value of 21.21 da 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 da, and put it, here, and done it this way instead. It's not even to do with the ties. It's more if I decide that I'm like, oh, I should add some other variable, then it would create a whole different thing, and it would I'd have to copy and paste again. So this method right here allows me to just reference this other object. So you'll see that by doing quint with the square bracket 1, that just spits out the first thing in that object. This is a vector, so it's like, remember, the vectors don't have multiple dimensions. It's just 1, so you don't need that comma and whatever. So again, I've taken this, I've stored in a 1 for anybody that had a propensity score less than 0.21. And I can even look at my data. And this should be all the, well, maybe I didn't do that. I swear it. Let me run it again. And try again. Here it is. So you'll see this new variable is here. It's got a few 1s, and then it's got some NAs as well for the people that aren't within that category. So then the next step is to then define the people that are in the second quintile. So this one's slightly more complicated in that we have to give it an inequality, like a greater than or less than on 2 sides, range for values on, or restricted on each side. So these people can be above or greater than or equal to the value of the first quintile, but they have to be less than the value of the second quintile. So this will define being in the second group. Basically within, this group is within 0.21 and 0.33. And then you do this for all of them until you create your 5 different categories. The highest one just being whether or not they're greater than or equal to this last quintile, because it's basically 0.54 all the way up to 1. And so this creates our 5 categories for the quintiles. Then I could do a table of this to look to see how good it did, splitting my people into even groups. Boom. Oops, what do you think? How do we do? It was really R that did it, not me. This is, I feel like this never happens where it's like, so no, it's because it's so, yeah, obviously there's, the number was not divisible by 5, so we don't get perfectly even groups, but this looks pretty good. So now we have these 5 different groups with the quintiles of the propensity score. So then what we can do is within each of the quintiles, we can compare different characteristics of the study participants. And so, for example, let's look overall. We'll just look at, this is the Apache score, I believe, this APS. So let's just look, to begin with, we'll look overall to look to see what the Apache score is among those that had right heart cath and those who didn't. Oops. I'm using the t-apply again. So how does the Apache score compare between those who had treatment and didn't. Yes. Higher in people that had cath, the right heart cath. But next, let's just look within each of those 5 quintiles. What would we expect to find once we restrict this comparison to each of the quintiles? Within a quintile 1, for example, what are we expecting? How will the Apache score differ by whether or not somebody got the right heart cath or not?
Should be close.
Yeah. So it should be closer to each other because these people are going to have similar propensities to getting the treatment. So this is the lowest one. So you can see it's like the median's like 38 to 42, still like 4 points away, but not 10 points away like it was previously. We can do it for the second quintile. What do you think about these ones? Like 44, 46, closer, very close in this third quintile, close in the fourth, and pretty close in the last one too. So much closer within, once we're within a quintile of the propensity score, the characteristics of the people are more similar, which is what we want, because we want to find, you know, areas where the groups are similar to each other. The people that were treated and not treated, to get rid of any confounding and things. Okay, so what are the different ways that we can apply a propensity score?
So I mean, there's matching, reverse probability weighting, quintile analysis, and there's more regression.
Yeah, putting it as a variable in your regression model too. Yep. So those are all different ways that we'll kind of go through how to apply that. Which method did the Connors paper use that we? Matching. Yeah. What type of matching did they do?
It was like next door neighbor.
I like that. The next door neighbor. Yeah. The nearest neighbor.
That's what it was, wasn't it? Something like that. What do you call it? Best
It's usually
neighbor?
nearest neighbor.
Nearest
They off,
neighbor.
but I like next door neighbor.
Next door neighbor.
Well, they did nearest neighbor or exact neighbor, and then they did a little bit, you know, like on the left side, positive. and
A
then
block
little-
A block away neighbor.
block away in each direction matched. Yeah.
So yeah, the matching, and there's a lot of options for how you match on your propensity score, and we'll go through a series of those, and I'll show you how they make your computer crash. Okay, so, and again, they used matching. So the first thing that we'll do, let's do the quintile one first. So basically, we're just going to adjust for those quintiles. We're going to include within our model our outcome will be whether or not somebody died. Then we're going to include whether or not they got right heart cath. And then we're also going to include the quintile variable in it so that we're adjusting for that. Can we put other things in our model too?
Yes.
Yes. Yes. Why would we maybe want to put other things in our model?
We haven't quite been able to figure that out yet.
Well, I think, for example, these guys, they put, so they have the propensity score and then they put the disease because, you know, the reviewers told them to do so.
Good a reason as any. No, that's not a good reason. You shouldn't just blindly follow reviewers.
I mean, to us, it made a lot of sense where it's kind of like stratified randomization to a certain extent, but when you look at the disease groups, even though you're putting you're matching by propensity score, but the reason behind the propensity score can be very different from one person to another.
Mm-hmm.
So in order to make sure broad brush categories that one septic patient looks similar to another septic patient, then you might want to add in the extra things above that.
Mm-hmm. Yeah, so it could be, I mean, there can still be some residual confounding and you still may want to adjust for something like that. Or there could be factors that you want to adjust for that like aren't necessarily predictors of the exposure or something like that that you could theoretically adjust for. So yeah, there could be residual confounding or other things that you want to adjust for. So yeah, it's reasonable to be able to do that. And I mean, the propensity score obviously isn't perfect. It doesn't like perfectly account for everything. So that's a way to, again, that kind of gets to the residual confounding. All right, so this model, all we need to, we already did the quintile recording, obviously, just above. So we just put the two variables. We have to treat it as a factor. We can run this, run our GLM, run our exponentiation. So let's actually just look at here. So what is our effect now for the right heart cath? What's the odds ratio? Has it gone up or down?
Down.
Down. So yeah, it's right here, 1.15 is our new odds ratio. So it's definitely attenuated a little bit from what it was before, although is it still significant? Yeah, it's like the p-value is like 0.02, so still significant. We may not, what happens in the paper after they adjusted for their propensity score or matched?
It went down.
Did it become non-significant?
Still significant.
Still significant, but less of an effect. So kind of seeing something similar here. And we don't really care about these coefficients or anything that go along with the quintiles. They're just a purpose for a way that we're adjusting for that. So we already talked about this. Oh, so you can also look at an interaction between the quintiles and the propensity score just by adding, you know, the interaction term. Why might we want to do that?
To show the effect of, I mean, I'm just regurgitating what you said on Monday. To show that the effect of the treatment is constant. Is that the one? To show the effect of the treatment is constant throughout
Across the quintiles. So it's like to see if the relationship between right heart cath and death changes depending on somebody's propensity to receive it, to receive right heart cath. So we're kind of like, we're allowing that to vary, the effect of the propensity score to vary depending on what quintile you're in, which again, remembering that each of the quintiles represents the probability that they'll be on treatment.
You want this to be null.
I mean, you don't necessarily, I don't know whether you have a value judgment. If it turns out to be different by it, I mean, that's something that you can report as well. I mean, it works. It would be like right heart cath works much better in the people that really need it or something like that, based on the propensity score.
So it's an interaction term. So you're multiplying your propensity score by the quintile.
So the propensity, the quintile is defined by the propensity score.
What are you multiplying?
If we want to look to see whether or not the effect of right heart cath changes by the quintiles, what would we be multiplying together?
Right heart cath times quintile.
Yes. They're the only two things in our model, so there's not a lot of
The right hand
options.
side is the outcome.
It's the outcome of the death is our outcome.
Oh, I see, because we're on the second part.
We're already on to the, yeah, we've moved past the creation of the propensity score. So this is, oh, I've got it right here. This GLM2A has the right heart cath, the quintiles, and then plus the multiplication of those to get at the interaction. So let's do the summary. All right, so how am I going to figure out whether or not this is significant, whether this effect of my interaction is significant? I've got 4 different estimates. How will I tell overall, globally, if it's significant?
It's got to be some sort of
Likelihood ratio test.
Boom. Likelihood ratio test. Did that come out of the ceiling?
Yeah.
Yes. Hi, ceiling.
God, too.
So yeah, we can do a likelihood ratio test. And what are the two models that we will compare?
Oh, one with and one without.
Yeah, so we'll compare this model to the one that we fit before that did not include our interaction. So that's part of some function or some package 2 that is called lm test with interaction. So yeah, oh, and I didn't even do this. So it's called lm test. Just to confuse you some more, Bab, I don't think that anywhere in the thing did I put lm test this time. So
Oh, yeah, I'm putting it right now.
all right, so the function is called lm test. Excuse me, the package is called lm test, but the function is called lr test. And then I just, as we mentioned, we just list those two different models. All right, so here is the results from this. So remember, we have the difference between the two is 4 degrees of freedom, because there are, remember, there's 5 categories, one's a reference. So the difference between the two models will be 4 different parameters. So what does our p-value say? Tell us.
Sorry, what package is LR test?
LM test for, I was reading it here, testing linear regression models. Although technically this isn't a linear regression model, yet it can do it anyways,
So which
because it's a likelihood based.
Are you comparing GLM2 to GLM2A?
That's correct. Because remember, 2 was the one that we had. 2 has the RHC and the factor of the quintiles. And then 2A has right heart cath, the factor, and the interaction between the two.
So I guess we reject. I mean, they look the same.
They look the same.
So, I mean, they're not.
The null hypothesis is that the two models came from the same distribution. With the p-value, we fail to reject the null hypothesis. So
Does that mean that we should include the interaction or no?
that's up to you.
Based on the significance? No, so the interaction
Doesn't
isn't
matter.
adding anything, so we don't need to. The results are not changing. The effect of right heart cath is not changing based on quintile or propensity score. So we can throw that away. We can drop the interaction. So we're still left with this 1.15. If we had decided that it was significant, how many different effects of right heart catheterization would we have? Yeah, we'd have to get one for each of the quintiles would have a different effect of right heart catheterization, which would obviously get a little bit complicated to like telling a coherent story with that.
But the quintiles were arbitrary, so you could do a global ANOVA and combine some of the, or not global ANOVA, but you'd go back to the LR test and combine some of the.
So usually, I mean, I like what you're thinking. Usually they keep it within the 5 different groups just because it's been shown that there's something like good about that. I can't remember what it was.
5 is not a magic number.
5 is not a magic number? Did you, like, okay.
No, I don't know.
In the notes, is this one is in our notes, the lab. We're on page 8.
Correct.
This stuff's not in there, right?
No, there's like a run code in R. Is there an interaction?
I'm just gonna.
How would we formally test this? There's reference to it.
So because the p-value is 0.79, then
Yeah.
there's no significant difference between the two models.
Uh-huh.
And so the interaction is
This literally is the effect. This is the p-value that goes with the interaction, just as a aside. We could also have, if we were interested to get a p-value just of the model, let's go back to the model without the interaction, but just of 5 or the quintile indicators. How would we get an overall p-value for these? These being those for different levels of the quintile that we have in the model.
That was the big A ANOVA.
Oh yeah, you could do a big ANOVA, although I'm not 100% sure that the big ANOVA works with GLM. I can't remember that off the top of my head. It may. Alternatively, we could do a likelihood ratio here too. We would just compare the model with only right heart cath to this model right here. And the difference between those models would be these 4 different levels or whatever, so of the quintiles. So that would give us that p-value.
Just again, null, I know we've done likelihood ratio test last week. The null hypothesis is that the models are giving this same information.
Yeah, the models are providing the same information. That's like a weird way to say that. But yes, that's the essence of it, yes. Or it can also be, or that there's no difference between the models. That's really what it is. No difference between the models. And it also, in addition to telling you whether or not there's a difference, this is the p-value for that interaction term, the global p-value for that interaction term. Yeah, this lab document was getting like super duper long. So that's why I have like reference to R. Go look in R. Okay. How are we doing with quintiles? Feeling okay about that? All right, so now we're going to look at just putting the propensity score into the model and adjusting for it. However, we're going to do it in the similar way that it was done in lecture on Monday, where rather than just using it as the probability score, the PF, we're going to do the logit of it, so the log odds, because that tends to be more linear. And not only that, but we're also going to do this restricted cubic spline, which is a way to also address nonlinearity. And I think it's been shown that this is like a good way to account for the lack of linearity by doing this cubic spline thing. The cubic spline, or a spline in general, allows you to have different slopes for a variable depending on different levels of the variable. Like it's kind of like a basic spline is like a stick. Do they even call it that? It's like a stick spline. I don't think that can't be what it's called, but it's like the 2-piece stick thing where it's like, hold on, I'll draw a picture. So here, imagine that this is age. And this over here is, let's just go with propensity score. So imagine that it's like for the younger groups of ages, maybe it's like there's only this like gradual association, but then once you reach a different age, it can like go up like this. So basically there's like 2 different slopes happening here. So a spline allows you to have 2 different slopes. I think it's important that we now Google to see what that name of that is. Spline stick.
I'm just hoping that there isn't something really bad about that too. Like the first thing that comes up is like Urban Dictionary with
Linear regression. Segmented regression. Maybe if I just type in spline linear regression. An introduction to splines. All right, well, I don't think I'm going to find the stick thing right now, but I really feel like there's something that has, occasionally it's called something related to a stick. Because it's like 2 different, anyway, I'm going to stop. So instead of just doing it as these like kind of straight lines, the cubic spline allows it to have a curve to it. And in fact, cubic, remember, that's a cube, so 3. So it allows it to have, I think it cuts trying to think for the cubic spline, how many cuts there are. But anyway, so it allows kind of a lot of flexibility with the shape of it. And because we're only interested in adjusting for this, we don't need to like get into the weeds of exactly why or like interpreting it or things like this. But the general idea being that this is a way to adjust for it, kind of adjust for the propensity score in a way that meets the assumption, like linearity assumptions and things like that. So in order to, so the first thing, because we're doing it of the logit, we first had to create the logit, which we've actually already done above. But remember, that was where we could, we take the propensity score and we that was a probability, and we use the equation to turn it back into the log odds. So when we're doing this spline, we put in the, again, we have whether or not they died as our outcome. Right heart cath is our predictor, our exposure. And then we're basically just adjusting for this spline part. So this spline means this RCS is a restricted cubic spline. This is our logit. Oh my gosh, I forget what the 4 is. I think that, I actually forget what the 4 is indicating. It's some parameter that you have to give it for the cubic spline. It might be the number, anyway, so it, we won't go into the weeds of that. It might be the number of knots, but I think that that's not, knots are like how many times it curves or changes direction.
Wait, what was RCS again?
Restricted cubic spline, and this appears to be part of a package that I didn't load. This is my problem here. You asked about packages. I'm like, oh, no big deal, and now I've lost all of my packages and forget what they are.
So the notes say it's in the RMS package, but even when I click on the RMS.
Oh, it's RCS package. Wait, RMS. Oh no, it does say RMS package.
Yeah. So even when I click on RMS package, it's saying that I can't find the function RCS.
Okay. Oh, well, I'm having the problem of that I had to reload R and so don't have this.
Do you get, I'm not quite getting, quintiles matching and inverse probability weighting, it kind of makes sense. I'm not quite sure what we're trying to do here.
We're just adjusting for propensity score.
Oh, so literally it's just a...
It's just like putting
So
propensity
linear
score into the model.
All right, so it's like, okay, it's literally that. And then to help it look linear, we're doing all of this other stuff.
Exactly.
Okay.
But yes, the underlying idea of it is that we're just adjusting for it.
And to meet the linearity assumption of regression.
Yes. And now I'm trying to figure out where I created the logit. Oh, here you are.
Segmented regression, also known as piecewise regression or broken stick regression.
Yes. Thank you, Henry.
Wikipedia.
I remember so bad saying it in Stats 1, but I couldn't remember the name of it. I just remembered
Broken stick. That's what it looks like. A twig that's broken. Anyway, so Jana, mine was running now, but I can't tell you why yours is not running. How are you doing? Are you sad? You sound sad.
It's
Maybe
still not working.
We can help you later.
It doesn't really matter.
RMS?
As long as it will work on my own computer. I
Right.
don't mind if it doesn't work on this one.
Well, let me know if it does not work on yours.
Okay.
At a later time.
Will do.
So this is the output now for this one that has basically just adjusted for the propensity score. We've got these three different additional things that are estimated based on this spline, but we don't need to worry much about that. The thing that we're worrying about is our estimate for our right heart cath and what the odds ratio is for that and whether or not it is significant. So what is our odds ratio? 1.13. And is it significant? 0.04. So we're still significant, although obviously less so than our unadjusted case. And again, we have relatively similar to when we adjusted for the quintile. All right, so that's adjustment. In the most simple way, we could have, if we hadn't been doing all of that linearity stuff, we could have just literally put in the propensity score, PS. That's like the basic premise of what we're doing. We've just done this, and we've like done some other stuff to make it meet the linearity, but that's the idea of that. All right, so
the fact that that the odds ratio is attenuated kind of towards the null suggests that there was confounding by indication for RHC. which
That's
is
correct,
what the
yes.
Propensity score is.
what does it mean? Who's getting our right heart cath? Is it people that are sicker or not sicker? Sicker, right. So they have a higher likelihood of dying. So that means if we hadn't adjusted for these other things, it would look like it's the right heart cath that's making them die, but it's actually just because they're sicker that they're getting the right heart cath, basically.
Or you could just say confounding by the propensity score.
Yeah, or confounding by like indication. You don't really say like confounding by the propensity score because that's like what does that mean?
Yeah.
Right, but yes, by the propensity for getting the treatment. All right, so next is inverse probability weighting. What is inverse probability weighting? 1 over. Literally 1 over, yes.
That's what I took away from that. It's just 1 over and then 1.
Yeah, so we weight them by 1 over whatever it is that 1 over the probability of whatever it is that they received. I'm trying to think if that was the right way to say that. So for basically, it's like for people that got the right heart cath, you do 1 over their propensity score. For people that didn't, you do 1 over 1 minus their propensity score. So you do the propensity almost of not getting it for the people that didn't get it. So we just need to define these inverse probability weights. So for those people, let me go to the R code. We'll start with the people that did get the RHC. So what I'm going to do, I'm going to create this new variable called IPW for inverse probability weight. And I'm going to say whenever, I'm going to kind of subset it or just define it for people that received right heart cath. That's what this first part is doing. And the second part is then saying what I want to assign to these people. So I want to assign to these people 1 over the propensity score. This second part right here is also restricting it to people who have received the right heart cath. If I were not to have this, if I didn't have this restriction here, it would not run because it needs to have the same number of people in both of these things. Let me quickly show you that. Hopefully this won't. So here I got rid of that subset, the second subset thing. And I don't even know what that just ran. Okay, so it gives me this error message that says number of items to replace is not a multiple of replacement link. That's code for we don't have the same number in each of them, so I can't replace this because the dimension or the length of this is only among the people that have received right heart cath. This was for everybody. So that means that I need to restrict both of these to those that receive right heart cath for this to run. So I will run this. This is now, if I look at my data set, hopefully this will be over here. So now I have the IPW for all of the people that got right heart cath. Then I need to do it for the people that did not receive right heart cath. So now I'm restricting it to those with a 0. And then I'm plugging in 1 over 1 minus the propensity score because that's the probability that they didn't get. It's basically the inverse of the probability that they didn't get the right heart cath, which is, they didn't get it. And again, restrict it to those that did not receive it. So this is how we create those inverse probability weights. Now it should be defined for everybody over here. Now we have one for everybody. And then, I just did like a t-apply to look at what the values of the inverse probability weights were by their treatment status, just to get an idea here. So for the 0s, those people that were not treated, their weights go between 1 and 9. And then for the people that were treated, it goes between 1 and 26. What causes somebody to have a high weight?
There's not very many of them.
Right, there are not very many of them. So it would be somebody would have a high weight. So let's first consider the, trying to think of, yeah, let's look at the treated ones. So if they have 1 over a very small value, so if they have a small value of their propensity score, that means that it's kind of predicting they would not have received right heart cath, but in actuality, they did receive right heart cath. Wait, am I doing it the wrong way?
No, that's right.
Okay, sorry. So that means they're going to get a big weight. So if we went all the way back to our picture, our histogram, so that would be, for example, somebody like right here. So this because there aren't very many of these people, this person would get like a larger weight.
Why would you do that?
That didn't make sense to me either, that you're giving high weight to people that might be like outliers or.
Like you want to smush everyone together.
So it's kind of you're creating like more balance between. So instead of having, or it's like you're creating more people over there so that you have more people to compare to the other group. So there's more like overlap. You can also do standardized weights where you like divide it by something as well to make it a little bit less extreme. Some people, so that somebody doesn't end up being weighted, like one person being weighted a really high amount and getting a lot of influence or something. The same idea. So if we go then to somebody who is not treated, but they have a really high propensity score, they're going to end up with a large weight because it's going to be 1 over 1 minus a big number, which will be a small number, and that will create a big one. So again, somebody over here is going to be weighted a lot more than somebody over here where there's, they're falling within the range of what's likely to happen. So yeah, that's
running all of this again in a regression model.
Yeah, so then we're going to run a logistic regression model, and we're going to apply these weights so that people will get different weights so that we kind of create more balance across that way. I was going to also, kind of wanted to plot this histogram. I was curious what this would look like. So histogram of IPW weight, where, stop being so smart, where right heart cath is equal to 1. Oh gosh, oh no, it's okay. So these are the weights for the treated group.
So to me, I would just say you can't use IPW.
Because what?
I mean, the numbers always seem to be fairly consistent, so it doesn't. The way this data is presented, it doesn't seem like you're gaining that much more from quintiles versus adjusting versus IPW, and those 3 things are all doing pretty similar stuff. And it's just sounds like semantics as to which way you want to do it.
So there are like strengths and limitations to each one, and obviously you shouldn't, well, not shouldn't, but typically it's not like you usually select 1 or 2 maybe at the beginning, or I mean, you could even do all of them, but you need to have some sort of rationale or whatever for what you're doing.
But I feel like it's the difference, that
in the answers
generate is like, because at the end you're just putting them into a linear regression. It's just how much weighting you give to each thing. So whereas you bump all the quintiles together, or you bump all the, or you make it look more like make sure it fills all the assumptions, or you smush everyone together in a inverse probability weighting. But in effect, they all do the same thing, right? So
there are ways that you can like adjust for the propensity score. They will not always give you the same answers, and there's, with matching especially, you might end up losing people.
So matching, I feel, is a completely different stroke better. I mean, the matching seems to be the best way that propensity scores to me.
But what about the fact that you lose people that you don't match?
It's a sacrifice you have to make.
But I mean, a sacrifice that may affect your validity.
You went from like 5,000 to 2,000 because they only matched. So are you saying that those other 3,000 people didn't matter?
And it's like you're most likely getting the people that don't match are kind of like interesting people, because it's like, why does this person have such a low probability of getting the treatment, but then they actually got it or something like that? So
why in the literature is there so much more matching as opposed to just not adjusting by the propensity score then?
I don't know if I can answer that. I don't know the answer to that, why people have tended to do that.
Yeah,
Maybe it's more of a like,
Because that's what Jeff said, 97, 98% of propensity models are used for matching.
yeah, maybe it's because it's like has a like matching is something people like understand. I feel like IPW is becoming more popular, or seeing that more often.
But it sounds really fancy initially before I tried reading this paper, because the paper that I was sent at Boston was just so dense, like put me off. So
Try reading the Rothman section on inverse probability weighting propensity.
But now
score.
the way you're teaching us, which makes it so much easier to understand, is it seems very small, minutiae. Like the first three does seem like they're only really, like, depending on you. So you've analyzed your data, and depending on the spread of your propensity score, you can really adjust. If you have a really large spread, and there's not that peak that you see in these ones, like, then maybe an inverse probability weighting is better because it'll squish everything together. And quintiles will be too, like, there isn't, I don't know. Whereas a person at the start of the quintile look different to the end of the quintile.
Right. There can be, the thing with quintiles is there can be like residual confounding within those quintiles. And that's why sometimes you might still adjust for other, that's one of those cases where you might adjust for it.
How would you a priori rationalize your use of IPW over quintiles? I think the adjustments like the surrogate between those two.
If you want to weigh kind of the outliers, the ones in which your probability was A, but instead they were B, then that's what you want to do, because if you wanted your final analysis to basically factor that in.
You're like almost creating like a pseudo people, fake people that are in your sample size, or that are in your sample that represent those people that you have a lot fewer of, so that you can kind of have a better comparison there. But yeah, there are, I mean, I can't tell you the answer. I'm keeping it secret. No, there is no like one single answer. And I think sometimes it's interesting to do a couple different ways. I think in some instances, it's still a field where they're like, oh, let's report it a few different ways to see how that compares and to better understand the methods of it and strengths and limitations. And it could vary, by your study or things like that. So we did, we haven't even fit our weights. Okay. Or we did our weights, but we have to actually run the model. Okay. So GLM, there's an option within it to include weights. So that's where we put the IPW. However, don't get too excited, because we're going to run it. And oh God. Did anybody else run it and get an error? It should give you a error, but mine stopped. Is anybody else's still running? Or do anything? Basically, when we use the idea is that if we use the binomial function, the binomial distribution, it can only have weights that are whole numbers. And remember, we have weights that are decimals. So if you just change the family to quasi-binomial, it will run that way and give valid answers. So you'll notice this is the model output right here. Hold on, I'm closing this one too. I'm on to a new one. Like how many R studios can I use in one class? Okay, and we only have 22 minutes left. Run. All right, so the thing, notice when you get the output for the this quasi-binomial, when we've applied the weights, we only get the one estimate. We only get right heart cath. So it's not like just by looking at this output, we can't necessarily tell how exactly the weights were applied or whatever, but because we put the weight, that means that it's been adjusted. And we'll see once we exponentiate, again, we're getting a very similar odds ratio, the 1.13. So similar answer with this as well. Any questions about that? No. All right, so then the final section is about different methods for matching. And this is my disclaimer. There are a few parts of this package that don't work as I want them to. And every year I go and check the package again right before this lab. And I'm like, please let it do the things I want it to do. And then it doesn't. And I haven't yet found a better, there's this one package called matching that actually might be work as well. It's just, it requires a lot more specification with like how close they can be to each other, as opposed to just being able to specify like nearest for our next door neighbor. For that other one, you have to specify how far away you want your neighbor and like how far, can they live in the floor above you? There's a lot of different like things to specify with the caliper. So it's a little bit more labor intensive. So match it is what we will continue to use for now. And we'll go through, hold on, let me load the package. Match it. So if anybody wants to write a package, Henry, to do appropriate matching, I'll give you a sticker. Oh, the other thing.
Although, I mean, I think it's a good point, though. It's interesting that you said there isn't something available that tells what you want it to do.
Right.
I feel like at some point there's.
Right. And that's why it's like every year I'm like, maybe this will be the year. And then no. Okay, so we'll start with the nearest neighbor thing, the next door neighbor, which is a type of greedy matching. Basically, it's like you start somewhere, you find a match, and you like hold on to that match, and you like don't let it go.
Oh, yeah.
You like find your partner for life, your match partner, and you don't let them go. And then you have to find like the closest one. There's like some sort of distance that it's using to find the closest one, and then it finds that, and then that person becomes unavailable to somebody else, even though it might be a better match.
That's quite funny, actually. I didn't think of it. So it's greedy because it's first come, first serve. So it depends on where you are in your data set.
Yes. So usually it's so we're going to randomly sort our data set and like give it a starting point so that it's not like just dependent upon who's right next to it. Maybe it's like enrolled people or certain whatever. And the other thing with whenever you do a random thing like that, where we randomly sort it, we're going to specify the seed, which is the starting point of the random sort, so that we can recreate the same results. Because if you don't do that every single time you did this, you'd get a different answer. Oh my God. All right, so it's not running. And so we can't even, it's not letting me load. Anybody else loading? Why is it just me? Why me? Well, it's because I have like 15 versions of R open. I don't even know which is the good one.
C5555.
Don't save. They'll freeze after a second. This was Quint. I remember you, Quint. All right, so I'll just walk through the lab document as opposed to waiting forever for this. Oh, it's a little unfortunate that, okay, so this is where I'm going to sort the data randomly by the propensity score. So the first thing that I did, hold on, I need to get rid of this stupid pen too. Actually, I like the pen. It gives me a weird, okay. So this very first thing that I did, I was just going to print out the first 10 observations of the propensity score just to see what order it was originally in. The next thing I do is setting the seed. That's the thing that I told you about where we wanted to make sure when it does the random sorting that it always uses the first thing so that we can recreate the same results. The next thing that I'm going to do, this is what does the sorting. I don't know whether, I'm not going to go into all of the details of this, but basically it's ordering it according, this random uniform is a uniform distribution, which means that you have the same likelihood of pulling any single value from it. So this is how it's sorting it in this order, basically. And then I'm creating this new data set that I called RHC_sort. And then just as a point of, just to see that it actually did something, that's why I'm going to print out the first 10 propensity scores of this one. This is all just getting the data ready to match it and making sure that we've randomly sorted it so that the nearest neighbor, the greedy nearest next door neighbor will be able to kind of recreate that the same time every way. And it will be a random selection too.
So do we have to always say set seed 555?
No.
What is the 555?
You can set the seed as anything you want. It's just telling it, basically there's like a random number generator thing happening and it's just telling you where to start from that, but it's still all random. It's just that this allows us to recreate the data, the same sorting every time.
That means that the random number that she generates is the same random number that you generate, and it's the same random number that you'll generate next time.
Yeah. So basically there's like this huge list of random numbers and we're going to start at number 555. And it's like, we'll continue, you know, in the same order after that randomly, but yes, on purpose, random on purpose. So then I had us install the package that didn't install. Let's check again. Oh, not that one. No. Okay. This is like unfortunate that this doesn't work because this one's like a little bit, there's some things happening here. Okay. So with the so this thing is called match it. That's what's going to do the matching for us. So the function is called match it. Within that, we put the equation for our propensity score. Not the propensity score. We put in that the same model that we had used. So we use RHC, squiggle all of the variables that I had included, the same ones that we had above. We tell it the data set we want to use, which is that sorted one. And then we tell it the type of matching we want to do. So we're doing the nearest neighbor here. And we save it into this thing. We want to save it into an object because this object technically is not yet the data set. We have to extract something from it to become the data set, which I'll show you. So this is this is straightforward. So this tells us our sample size, how many we matched and how many we didn't match, whether they were control or treated. So how many are we throwing away by not being able to match? What? Yeah. So 1368 we're throwing away, and those people were in the control arm. Those were people not receiving right heart cath. So we were able to match this we matched all 2183 that are in receive the treatment with that many controls. So obviously we're losing this many. Oh, this is sad. There are these cool plots that we could have looked at, but we can't look at them. Oh, so it gives you just an idea of what the propensity scores were in like unmatched, matched, like all the different groups. It's like the exposed, unexposed, and the matched. So you see like just the spread of where they are. Okay, then as the next step, this is where we have to create the data frame based upon that matched data set, basically, or that matching that we just did. So if we do match.data of the match one, which was that matching object we just did, this will create a data frame out of that. That will extract the information that we need, match.one. And I'm calling, or excuse me, match.data. And I'm going to call this data set RHC_match1 to indicate this is the matching data set the first one that we created. Then we can fit a logistic regression model using this matched data set, and we can get an estimate. Do you notice anything? What different would you maybe have wanted to do based on this matched data set that we created? How would we want to analyze this? Yeah, so you're getting at the fact that there's like maybe a conditional logistic regression because there's matching here. This is where I don't like this package because it does not tell us, it doesn't give us what I would call like a subclass in what other components of this package call a subclass, where it tells you who it was matched to in an easy format. There is a, why don't you work? There is a thing where it tells you what row each person was matched to, but there's not a way to like easily link it to each other to create a variable where it shows you exactly who's matched with who. So there isn't a way that I can easily see that we can do a conditional regression because I don't know who's matched with who, or a conditional logistic regression. So that's
wrong.
huh?
I don't like that.
Right. So it's annoying. That's annoying.
So at present, you just take the computer's word for it.
No, I'm not even. I'm saying the computer. What do you mean by I'm taking the computer's
No,
word?
he's assuming you are doing logistic regression, and you're saying conditional. And
Right.
You're saying you can't do conditional.
I can't do logistic conditional because I don't know what the matching element. I don't know how people are paired. I want to do conditional logistic regression, but this package has not given me the match, the person to who it's matched to.
Oh, so then you have to.
So I'm just doing a non-conditional, which is tisk, Angie.
Then you can't do it.
I'm getting the same answer that I got for everything else.
Okay, fair enough.
No, actually, I get 1.18. Okay, so that it's just the nearest neighbor that doesn't give us the subgroup, the match, because the other types of matching will tell you who it's matched to, which doesn't make sense. But they have their separate problems in that they cause your computer to crash. So optimal matching, what does optimal matching do? So it's, you're allowed, oh, go.
Well, so in greedy matching, A matches with A because they're exactly alike, but they can never be unmatched. In optimal matching, they say, well, A may have matched with A, but we can undo this because A matches with B and this other A can match with C. And so these two matches are better than that one exceptional match. And so it finds the optimal number of best pairs.
It is not greedy. It will let go of your neighbor if you find a better match, basically. I like always think of this as like romance, and it's like
Yeah,
you're allowed to like divorce from the person if you find somebody else.
So it's like Gilligan's Island, like two might be perfect for each other, but
Bless you.
like apart they make better or acceptable matches. And anyway,
Yeah. So this one, it finds a better. You're going to find a closer match. The problem is with at least with this data set with 5,000 and something observations, it crashes. So I restricted it to 1,000 participants just as to see what the results would be, and it does work with 1,000. So here is, it's kind of the same type of, the one thing that you specify is this method, I just changed it to be optimal instead of nearest. It gives you this warning where it's like the order of the match is not guaranteed to be within the same as your data set. I think we're okay with this. Without the data argument, I gave it a data argument, so I'm not really sure why it's in a bad mood about that. Again, it tells you we're down to 1,000, so it's a slightly different numbers than before, but we do get a match for, you know, every one of the treated people, we end up with a match. And these matches are going to be closer together. We could do the same thing where we look at the plots and whatnot, but we can't do that. And then in this case, it actually gives you this thing called subclass. Oh, hold on, let me go back to this. We have to, just like before, we have to do this match.data to extract the data from the match object, basically. And this one gives us this variable called subclass, which is who it's matched to. So this allows us to do a conditional logistic regression and to calculate whatever. So this is our remember the conditional logistic is CL1, and this is actually part of the survival package. So another relatively similar, although not, what is a p-value? Not significant, 0.5 here, although again, we only have 1,000 people as opposed to 5,000.
Where's the p-value?
Say that again.
Where is the p-value?
It's with the output. The output for the conditional logistic is slightly different, but it's this PR, this. It's 0.506. There's also full matching, which will match everybody. That means you can have more, you can have like 2 to 1 or something like that, so that everybody ends up with a match. This one also causes it to explode or to crash, so I'm also using 1,000 again. Everybody's matched. This one also will create the subclass, so we can do a conditional logistic regression. We end up, this one, the odds ratio is a little higher, 1.2, but p-value not significant. And then the final one is the exact matching. This one you can actually run on the full data set, except that we immediately get this error that says no units were matched. Why do we think that is when you're doing the exact matching? Nobody has the exact same propensity score, exactly. Nobody has all the same variables on everything that we've included. Just out of curiosity, I did this version where I used in fewer categories. So I just used age, sex, and I think this is their primary disease right here, and did the exact matching. And it actually did match some people. We had 45 and 46. Apparently you can have 2 to 1 here too. But so yeah, if you had fewer categories or fewer variables, it'd be easier to get an exact match, but then our propensity score probably wouldn't be as good. So sorry that we didn't get to see how the matching things. It's very frustrating. It's like the optimal and the full matching don't crash because the data set's too big. And then the greedy or the nearest neighbor one doesn't give us the subclass so that we can't figure out who matched to who to do a conditional logistic regression. So not ideal, but this is one of the few matching packages that I've been able to find that does kind of almost does all the things we want it to.
So we didn't match by propensity score.
Essentially, it's doing this, it's creating the propensity score for us, basically, by giving it all of the variables. I've tried it also by putting in the propensity score instead. And it gives, depending on which method, some of them give slightly different results. But yeah, the general idea is that you should be able to put in the variables that went into your propensity score. But it's doing the same, because we're doing all the same variables that went into the propensity score and stuff, it's like the same, more or less the same idea. Yeah. So here are all the different answers that we got. What do you guys think about, how do we interpret all this? What's our takeaway message? Oh, I have one more thing before I also created a model that adjusted for all the same, that just included right heart cath, and then I just put in every single variable that was in the propensity score, but didn't create a propensity score, just to see how that would compare. That was, the odds ratio there was 1.15. So within the range of all these. So was there confounding by indication, do we think? Yeah, there was definitely some attenuation there. We might have had even more attenuation had we put more things in our propensity score model, but I made kind of a smaller, limited version. How do we know which method to use? I guess we've already talked about this a little bit, but how exactly, which one should we apply? How do we adjust or apply the propensity score? Well, it seems like the matching ones, even though Bob really likes the idea of the matching package is not serving us well in R. But we shouldn't just base our decision based on coding options. We should do the best one methodologically that we think. Again, often people will present it maybe 2 different ways or something. And then, if it has different results, then you present it both ways and say, this is, what we found. But I do some caution with the matching because you can lose people if it were to work.
The sort of crude things that came up in study design, basically, because here they would have got the same conclusion using a multivariable logistic regression
Yeah.
as to is when the outcome of interest is rare.
Mm-hmm.
So that is when inverse probability weighting or when propensity score is a useful technique to use.
When it really shines.
Yeah.
Right, when the outcome is relatively rare for those of you at home. In case you didn't hear that.
So that was the thing that came up in our study design. With regards to just, the thesis, because for the thesis stuff, you can be a little bit more creative because you have just things that you're going to put through publication,
Mm-hmm.
and that will, for most of us, will be a logistic regression or a proportionalized model. For the thesis, say my secondary outcome is the number that go on to get a transplant.
Mm-hmm.
So only 20% of people in my data get a transplant.
Mm-hmm.
Now, could I, just for giggles, run a propensity model, propensity score analysis on just for that? So your likelihood of having a positive PSA, and so for my my likelihood of exposure based on
What's your exposure? The transplant?
positive prostate screen.
Is that your exposure then for something else?
So that's my exposure. So positive prostate cancer screen versus negative.
Uh-huh.
And then I'm looking, my primary outcome is who gets listed. And then my secondary outcome is who goes on to get transplanted.
Mm-hmm.
So,
That's kind of a weird, I feel like that's kind of a weird thing to do a propensity score
yeah,
of.
you really couldn't, because because everyone's getting tested. So
Right,
you either get a positive or a negative result.
right. And
That's
it's
not
not
good.
like that's confounded, but I mean,
Yeah, there's confounders. I didn't realize that. But like age is a confounder, or your probability of having a positive versus negative.
right. I guess, I mean, like there are things that will predict that, I guess, and then also be associated with
Yeah.
the, whatever your outcome is. But yeah, usually propensity scores are done in situations where there's like confounding by indication, which would mean there's some sort of like treatment exposure type thing that
Like a
people are
treatment
getting.
decision, like you're
Yeah.
not sure about treatment decisions.
Right, and you're basing it upon, somebody's, how sick they are or something like that.
Okay.
And that could also be a confounder of whatever that, like dying if somebody's more sick, like in this situation. Somebody's more likely to get a right heart cath if they're sick, and then they're more likely to die. Because you want to like isolate the effect of whether or not the treatment's working. Whereas I don't know, like whether or not your screening is I don't know. I'm trying to understand what the positive, negative screen.
I guess the ideal scenario would be those who get screened, and the propensity model for those who got screened versus those who didn't get screened. But for me, everyone got screened.
Yeah,
So
yeah,
then I'm just predicting based on covariance the probability of having a positive screen, which is not that useful. And then
right.
based on that, you're downstream. I mean, it'd be easy to do
Right.
a propensity score. It'd be very, very easy to do.
As long as you don't match.
As long as they don't match.
Yeah, I mean, actually building your propensity score is easy, like mechanically, but I mean, thinking about what goes into it and whether or not it's appropriate to use it and making sure you don't put downstream things on it and stuff like that is the harder part. So not a cure-all, but a way to adjust for confounding. And a nice way to do it, like rather than having a bunch of dimensions, like we were saying, like if you only have a relatively rare outcome, you're not using all your degrees of freedom, wasting them on everything in your propensity score. You could just use like 1 or 2 variables or something instead of 10, 20. Alrighty. Thanks for coming, everybody. There's a homework that I'll post today. 2 weeks. I think you have a quiz you have 2 weeks to do it though. There's a quiz on Monday. Right?
Yes.
Does that sound like something you're aware of?
Yeah, yes.
But then there's like something else. President's Day. That's not what it's called.
Patriot.
Patriots Day. And then you won't have class.
Did you get their corrected form back?
Are you talking about me?
Well, your email said it was there. Like,
Everybody, yeah.
Solution
Tamar
for-
said that it was. I put it on everybody's page, but
I don't
will
have-
somebody show me their page? Because I see it. I have like a different. It looks different when I.
That's it. It just says submitted. So previously